Okay, perfect. So I'm glad to announce today's speaker, Professor Sergey Agafonov, and he will speak about hexagonal circular three webs with polar curves of degree 3. And please keep in mind that you can see the slides of beautiful pictures during the lecture following this reference. Okay, Sergey.
Many years, I'm very glad that I have this opportunity to translate my modest results over half of the globe. Well, this is the address of the file. Actually, the essential part will be in the, well, that you will need is in the end, where I will present the representatives of the orbits of the classification, and the first part I will try to reproduce on the blackboard. But you can see the pictures in the better quality made by computer or in these files. Well, my talk is a bit of off topic for this seminar. I will present only one very simple differential equation, and everyone can easily solve it. But I hope you would like the pictures. So in 1928, Bляшke and Boll published the first large monograph on the web theory.
Это недавний смел, который более жирно пишет. Да, вы толстая. Ага. Может,
First monograph on the web theory, which is still the main reference on this era of differential geometry. And in this book, they have collected a lot of problems. Not all of them were new. But many of them are still open. One of these problems is to describe hexagonal three webs of circles. Or I will call them circular hexagonal three webs. Now I will explain what means every word in this type and this problem. I will explain it with an example. You can now open the first pages of this file. I will start with an example, which is my simple to explain. So let us consider a circle and fix on this circle 3 points. Then each pair of points will define a one-parameter family of circles that are passing through this chosen pair. Well, if you consider this one-parameter family of circles on this file, it's in red. You will not have a foliation because you have these singular points. So you will have a single foliation. But inside these fixed circles, you will have a foliation by red circles. Now let us make the same thing with the other two pairs of points. The same thing, you will not have foliations, but inside this circle you will have 3 different foliations, and at any point the leaves of these foliations are transverse. So we will call this 3 foliations in general position. So this is a 3-web. Circular means that all the leaves of all 3 foliations are circles. We don't care which is the radii of these circles, they're circles. And the most restricted is the hexagonality of this circle. So this can be explained in different ways. So the one can be the most simplest, that these three foliations you can parallelize at the same by local diffeomorphism. So it's diffeomorphic to three families of parallel lines. So it's real restriction. Then in differential generic terms, you calculate some two form, which is called Blaschke curvature, and this curvature should vanish identically. Or it can be explained by some incidence relations, which give the name hexagonal. What does it mean? You choose a point. Through this point, you have three leaves, first, second, and the third foliations. Then choose a point, well, let's call this origin, at some point on, say, first line. First, well, the line, the leaf of the foliation of the first family. Let's call it P. Then you can draw the line through this P, the line of the curve of the second foliation, till it intersects the third. Then you swap the family to the first, and you continue this process. Since the leaves are in general position, so they are transverse, and if the point P is sufficiently close to our origin, you always come to the same leaf, but not always to the same point. So if all these figures, hexagonal-like figures, are close for any choice of 2 points or on any leaf of any foliation of any family, then it's called hexagon. So we will have hexagonal-like pictures, and you can see this on the file. This hexagon is marked by black. Or you can reformulate this, that you take a sufficiently small curvilinear triangle whose sides are arcs of the leaves, and you can complete it to the hexagon. So this is very restrictive, and the problem to describe all such webs made of cells, hexagonal webs of cells, is still open. So what was the progress? Before I start talking about the known examples, let me say a few words about the right context for studying such webs. The right context for studying such webs is Lie sphere geometry, sometimes called projective Nobel's model of so we will project our circles, our 3-web, from the plane to unit sphere by stereographic projection. Then it's well known that well, we will apply inverse stereographic projection. Right? Then it's well known from the first course in complex analysis, then the image of any circle in the plane under inverse stereographic projection is a circle. So our 3-web of circles in the plane will be mapped to hexagonal 3-web of circles on the unit sphere. What is the advantage of this approach? First, well, we would like to classify all such three webs up to Nobel's transformation, and Nobel's transformation can map a circle into a straight line. Sometimes this, straight lines are considered as circles of infinite radius. Then in this model, you don't distinguish between circles and lines because the image of a line is a circle passing through the projection center. So we will consider the problem of describing hexagonal three webs of circles on the unit sphere. Well, this unit sphere we'll use also to describe circles, in which way. So we have a unit sphere and a circle of this unit sphere. This circle is a section of the sphere by the plane. This unit sphere sometimes called in this model double quadratic because you can replace it by any smooth quadratic and develop the same type of geometry. And then this double quadratic defines a duality. Then this circle is a section by a plane. This plane has a dual object, which is a point. This point outside a unit sphere. This is a polar point of this circle. Well, to construct this polar point of a circle, you can construct a geometrical. You consider one parametric family of tangent lanes to the double quadratic at points of the circle. You have one parametric family of planes. It envelopes a cone, and the vertex of this cone is this point. We'll call it polar point of the circle. Then, if you have a one parametric family of circles, for each circle there is a point, you have a curve outside the double quadratic. Well, we have through each point we have three circles. So we have 3 points corresponding to 3 circles through the points, and through each of these points passes.
Сергей, секундочку. Люди жалуют, что звука нет. Прерывание бывает. Ну что, перейдем на... Картинки там есть.
Вроде бы есть.
Картинки там есть.
Все слышно и видно.
Ну давайте мы сейчас другой микрофон возьмем, испытанный. Подождите немножко. Концепция изменилась. Так. Так, это вам.
Нужно его активировать, или он уже работает?
Работает, да.
Then 3 web is a 3 family of circles. So to each family corresponds one parameter family of circles. That means that 3-web is given by, well, locally by 3 polar arcs. And how then to find the circles passing through some point P on the sphere? You draw tangent plane to the unit sphere. This plane will intersect each arc at some point. Each point defines a circle. So we have 3 leaves of our 3-web. Then it's quite natural to pose the following problem. Let us look for hexagonal 3-webs so that these curves, well, they're defined here locally, but we can pose the condition that the union of these arcs belong to the same algebraic curve of degree 3. Then it's quite natural, right? Through each point, there is a tangent plane. Tangent plane intersects algebraic curve of degree 3 and 3 points. These 3 points define 3 circles. We have a 3-web. So what is the condition on this? We'll call it polar curve of the 3-web. What is the condition of on this polar curve that guarantees that our 3-web is hexagonal? Well, it's interesting that in this formulation, I have not found this discussion in the book of Blyashke, though it's quite natural, and it's resembles the famous theorem in web theory, the Graf-Zaurer theory. So what examples are known for such 3-webs? It turns out that actually all the examples, all the known examples are of not exactly of that type, but of the type that the polar curve is always algebraic. It's not usually irreducible, so it can be collection of algebraic reduced components. So the largest family of examples was given by Volk in 1992, and from a bit of different point of view by Strubecker. And their construction, well, in this terminology is can be described very simple. Let us consider some plane and any cubic on this plane. Then this cubic is a polar curve of some hexagonal circular 3-web. So why is it so? If you consider tangent plane to Darboux quadratic at some point, this plane will cut cubic in 3 points, and it's well known that this you can introduce a parameter on this algebraic cubic locally, that these parameters u, v, and w, so their sum is 0. But this parameter u is a first integral of first foliation, right? This parameter v is the first integral of the second foliation, and this is a first integral of the third foliation. And this is nothing else than the structure of abelian group on smooth cubic. These are abelian integrals. Actually, this curve should not be smooth cubic. This cubic can be 3 lines. It can be smooth conic and a line. It can be singular cubic, right? So something like this or like this. Any cubic, any plane cubic will define a hexagonal 3 web. So this is this theorem actually has many names. It's a Grafenzaur theorem or Schall theorem in algebraic geometry, or 9-point theorem, which is dual formulation of Schall theorem in algebraic geometry. So this is actually the largest class of known hexagonal circular 3 webs. Well, what would be the next simplest case? The next simplest case would be to consider 3 lines. 3 lines, well, if these 3 lines are coplanar, we know from results of Wolks and Strubecker, Strubecker 31. If they are coplanar, this is a cubic, right? It's product of 3 linear forms. Then it's always hexagonal. So we will, the non-trivial case is when these 3 lines are not coplanar. So at least, well, they can intersect and not be in the same plane, or 2 of them are skew lines. And this problem was discussed by Blyashky in his second book, large book on web theory, Introduction to Web Theory, which is much more elementary and simple than the first book. So he posed this problem. He discussed it, but he did not give a solution. He said that it can be reduced to some algebraic problem, but this problem is so complicated. Actually, this computational approach would work if you use nowadays something like Maple or mathematics, these computer programs. So now you can go through this calculation using some tricks. I checked it, but it was not the way that the problem was actually resolved. So this problem was resolved finally by 1977. The full list of such 3 webs whose polar curve splits into 3 non-coplanar lines was found. Well, what are examples? So the first example is the one I started with. So it was actually was found by Blyashky student. So I don't remember the name of the student, but Blyashky gives his name. And then I have to mention the paper of Wunderlich. It seems that this paper was not known to the Soviet school working on web theory. So he has given the following 2 constructions, which always produce the hexagonal 3 webs of circles, and at least 5 of 10 forms found by 77 can be constructed using this observation of Wunderlich. So Wunderlich in this same year, 38, published a paper where he discusses very interesting 3 web, but well, I will mention this 3 web of circles a bit later, but he observed the following. The following construction always give hexagonal three-web of circles. You take two lines, L1, L2, which are dual with respect to Darboux quadrant. And take a and then take a third line which intersect these two pair of dual lines. And this construction is always gives hexagonal three web. It's a simple calculation, but well, some examples which can be produced by this very simple construction was rediscovered by Balabanova, Lazareva. And then, well, what are the geometry behind these dual lines? Actually, well, you take 2 points and consider the lines, the circles are started with the family of circles passing through 2 lines. To this family corresponds a polar line which is elliptic. So let L1 be elliptic, which doesn't meet the Darboux quadrant. So there is a natural invariant. If you have a line and a Darboux quadrant, it can miss it, can be tangent, and can intersect it transversely, right? So if it misses the Darboux quadrant, our unit sphere, then it's called elliptic. Then in the plane, as well on this sphere, it consists of family of circles passing through 2 fixed points. What is dual? Dual is the family of circles which intersect this family orthogonally. It's orthogonal trajectories. So these are dual. And the third one, well, intersect these two. It can be also, this one, which is orthogonal, corresponds to a line which intersect the Darboux quadrant. And the third one can be tangent, can intersect, or can miss it. So you have at least 3 examples which are not Möbius equivalent. So of course, we will consider all these webs up to Möbius transformation. By Möbius transformation in least sphere geometry, we will understand the projective transformation of projective 3 space preserving the Darboux quadrant. So this is essentially SO31 group. So this is this construction will give 4 of the 10 forms. Then Wunderlich also gives another construction which works for any foliations, not necessarily for circles. So consider 2 arcs of curves which intersect transversely, and consider one parametric group of transformation, so vector field and its flow, which is at this point P transverse to both of them. So you translate first curve, you have a foliation. You translate the third curve by this group. You have the second foliation, and you have a trajectories. You have a 3-web, and this 3-web is always hexagonal. It doesn't matter what is this group, what are these arcs. But if you take one arc, circle or straight line, the second circle or straight line, and group of rotation, so that the trajectories are circles, or translation, trajectories are straight lines, which are, of course, circles in Möbius geometry, or dilatation, homothety, the trajectories are always straight lines. So you have hexagonal 3-web of circles. there is a small problem to choose these arcs so that you will get 3 lines as a polar curve. Because this construction is rather general, you can get more general hexagonal 3 webs, so that polar curve is not a is a union of 3 straight lines. This construction will give also some examples in my classification, of which I will say I will talk later. So Bляшke, Wunderlich, then was Balabanova. Actually, she just rediscovered examples which could be produced by these 2 constructions of Wunderlich. Then there was some examples of Turkish mathematician Erdogan. And finally, Lazareva. She has found very non-trivial example of such 3 webs. So finally, the list consists of 10 forms. 9 of them are just points, in the sense that we classify orbits. So the orbit is just a point, and one is one parameter family of orbits. We classify up to Möbius transformation. So in the space of orbits, we have 9 points and 1 curve.
Sergey, may I ask a question?
Of course.
Zhenya Ferakonda. So I didn't get, is there classification of these triples of lines which produce hexagonal web? Lines, is there classification? You gave an example with number 1, right? But is there classification of all such triples of lines?
Yes.
That produce? So what's the answer?
Well, I have not prepared the pictures for this talk, but I will talk about this right now.
So there is a classification of when
Yes.
this polar curve consists of 3 lines,
which are
there
not
is a
complete now.
yeah, okay.
Well, there is classification. Actually, this is a list which was already obtained by 1977. And there was a first attempt to prove that this list is complete by this Turkish mathematician Erdogan. It was in 1989. Well, the proof was not complete because it was, well, he mentioned some calculation. This calculation was not presented. I checked this calculation by Maple. It's wrong. So, and actually afterwards he admitted that there is no proof. So this classification, this proof was actually settled by Shelikhov. Uh, 2004, 2005, sorry. Well, his idea was to look into the singular set of such webs. So it was a very clever idea, and by actually quasi-elementary methods, you will get a classification. Not only prove that this list is complete, you actually reproduce all the webs. So let me announce his, let's call it lemma of Shelikhov. This lemma is actually applies to any hexagonal 3 web, and it claims the following: you have a hexagonal 3 web, which is say, given by three-directional field, C1, C2, C3, and we consider the simplest singularities. Simplest not in the technical meaning of the singularity theory, but the, well, the following. We have a point P0, and in this point, the two directional fields are transverse. So C1 and Psi1 and Psi2. Well, we suppose that in the vicinity of this point P0, these directional fields don't have any singularities. So you don't have these points for elliptic pencils, right? So these locally, these are just three ordinary differential equations in a plane. You have tripellation. But at this point, Xi1 equals Xi3. So Xi1 and Xi3 are coincides in this point. And your web is hexagonal. Then either you have the following situation. Leaves of directional field Psi1 and Psi3 coincides. Or Psi1 equals Psi3 along the leaf of Psi2 through the point P0. So this lemma applies to any hexagonal three web. And well, let me prove it, because the proof of Shelikhov unfortunately was incomplete. He used these canonical integrals that parallelizes three web, but these canonical integrals typically they don't exist at singular points. So it's not difficult to find counterexample to his proof. So, but proof is actually elementary. So Psi1 and Psi2 are transverse. So we can suppose that Psi1 is dV. So this is U, this is V, local coordinates, and Psi2 is du. Then Psi3 is, well, it's equal to Psi1 at point P0. Wow, P0 is U0, V0. And this function at P0 vanishes. Just one point, right? But you have a condition of hexagonality. So the Blaschke coverage is 0 is equivalent that the following derivative is 0. This is logarithmic derivative. Well, you derive with respect to U logarithmic derivative of J, right? Well, it's very easy to integrate it. So it's just some function of U multiplied by some function of V. And now the proof is immediate, right? Either this or this should vanish at the point P0, right? So if R of U0 is 0, then you have coinciding these leaves, right? This is 0. along this leaf. Or if this vanishes in for V0, you have something like along the leaf of Psi2, V is constant, right, along this leaf. So it stays 0. Wow, this elementary lemma actually allows to construct all these hexagonal 3 webs whose polar curve is a union of 3 straight lines. Well, but actually, this lemma works very well also for the case which I'm interested in, when the polar curve is algebraic of degree 3. Wow, algebraic curves of degree in space, what are they? So the simplest case, 3 lines, right? So this classification was settled by Shelikhov, right? These 3 lines can be coplanar or non-coplanar, or it can be conic.
Sergey, I'm sorry again. Sergey,
All right.
but what's the answer? What are these 3 lines? What's their geometry?
Well, geometry, I was trying to find it in terms of duality with respect to Darboux quadratic, with respect to the corresponding symmetries of these lines, and I have not found any satisfactory answer.
But can they be at least all pairwise skew? No intersections.
Well,
Can they be all skew?
I will give you the simplest example. You consider the unit sphere centered in the origin, and the 3 coordinate lines are polar curves. This is one of the examples.
So they can be skew. They do not need to intersect.
Well, construction of Wunderlich will give you example with skew lines. Of course, there are skew lines.
No, but the third one intersects these skew lines. But
If
I'm asking, is it possible to take 3 skew lines?
all 3 are
produce
skew. No.
all of them skew.
No, if I remember right, all 3 cannot be skew. So one of the lines will intersect. Well, the third line. Well, if 2 are skew, the third will intersect one of them. It follows from Shelikhov lemma.
Okay. Mm-hmm.
But well, I have not found an answer, well, which would be nice in terms of geometry. So you can actually consider 4 webs, 6 webs, and whose polar curve is a collection of lines. And then from these 4 webs and 6 webs, choose 3 subwebs, which are hexagonal. Actually, all 3 subwebs are hexagonal. And for these webs, which are not 3 webs, but 3 subwebs are hexagonal, there are some pictures. For example, the lines are dual. They form a dual simplex with respect to Darboux quadratic. So this type of answers can be, but not all. So there are some tricky examples which don't fit this construction. So there can be conic and a line, right? This conic and line can be coplanar, or line can intersect the plane of the conic. What else can be? Well, there is a twisted cubic, right? And there is a planar cubic. Well, the case of planar cubic was settled by Folk and Strubecker. 3 lines is already settled by Shelikhov. Well, and all the others who contributed to construct the list. Actually, I believe that Shelikhov observed this property, then formulated it as a lemma. And so my contribution is the following. I claim that there is no hexagonal 3-web whose polar curve is a twisted cubic, and it can be proved using Shelikhov lemma. And I've got a classification of hexagonal 3-webs whose polar line is a conic and a line. So this is the list of all possible algebraic curves in space of degree 3. So we have a full classification. Well, let me say a few words about how to get, well, this is a bit simpler to explain how it works, the Shelikhov lemma. So we have a plane where the plane of the polar conic. So we have a conic and a line. If the line lies in this plane, the web is automatically hexagonal due to results of Folk and Strubecker. So we have a line which is not coplanar. So we have a Darboux quadric. Well, if this plane of the conic intersect Darboux quadric, it intersected in a circle, then the dual point of this circle must be on this line. It follows from the Shelikhov lemma. So let me mention the following thing. What is non-trivial consequence of the Shelikhov lemma? Non-trivial consequence is that this line, well, how we can obtain this simplest singularity? It appears when the line joining 2 points, one on the one polar arc, the other on the other, is tangent to the Darboux quadric, right? So then the corresponding circles are tangent. Then, well, if there is one line, there is a one parameter family of such lines. Non-trivial restriction is that this line of singular points, must be circle. It is the leaf of the third foliation. So the corresponding point must be here, right? All right. Then let us consider a point here on the line. Where are these 4 singular points on the Darboux quadric? You project, you consider the cone of tangent lines from this running point on the line, and this family of tangent lines is a cone. It's intersection of this cone with the plane of the polar conic is a conic, right? So you have 4 points. Well, some points could be complex, but there are 4 of them. If your point is running along the polar line, you have a 1 parameter family of conics, which intersect our polar conic in 4 lines. if all these intersection points are not moving along the polar conic, then polar conic belongs to pencil. This pencil of, let's call them running conics, right? You can check for each configuration, possible configuration, if this web is hexagonal or not. Then, in the case when at least one of these points are moving, when you move the point R along the line, then what will happen? We have here a circle, then the tangent plane to Darboux quadratic at this point will intersect the running conic CR. At one point, it's a tangent. It will intersect the plane P at a line, but from the construction, it's easily seen that it's a tangent to running conic, right? But then for all these points, the polar point of this circle must be here on the conic. So all these tangent lines is a pencil of lines, and the center belongs to the polar conic. So this simple elementary actually consideration will give you a construction. So you start with this polar point of singular circle T0. You project from this line L the contour of this Darboux sphere. You have one family of conics, and then you draw the tangent lines to these conics, and the tangent points will give you polar conic CP. So how it works in the simplest case, let us consider the case when the line is hyperbolic and the P the plane of the polar conic doesn't intersect the Darboux quadratic. Then, using Möbius transformation, we can send this plane of the conic to the infinity, right? So the P is in infinity. Then the infinity plane intersect Darboux quadratic in a complex point, right? And then the dual is the center of the Darboux quadratic, our unit sphere. That means that we can apply the Shellyhov lemma to complexification of the three web. Then our line, hyperbolic line, should pass through the center of the sphere. We still have a rotation, and by free rotation, we can make this line vertical, say in coordinates, affine coordinates x, y, z. So let us consider a point here, R, running point, and the family of tangent cones. Then what will we have at this infinite plane? You will have a family of concentric points, circles. Then this is a point, this point corresponding to the singular circle. You draw tangent lines. So these tangent lines are tangent to the circles, family of concentric circles, along which curve? It's a circle, right? It's a school geometry theorem. This is the circle passing through the common center of this family of concentric circles, and this point, which is a polar point of a singular circle. And this is the first example of my classification, which you can see in this file. Well, unfortunately, there is a password, which I don't know.
You mean hyperbolic pencil?
Yeah, the first one. This corresponds to this.
Yes.
Yeah, it doesn't look so symmetric, right? So sometimes the family of these running conics is not a pencil. So in this case, you have a pencil of conics. The concentric circles, they make a pencil. It's not always the case, but when it's not a pencil, then the web is not hexagonal. So this is a experimental fact, which must have some more rational explanation. Then, well, the natural question is if all the known examples fit into this problem, that the polar curve is algebraic of degree 3. The answer is not. So there are examples when the polar curve is not, there are no examples when the polar curve is not algebraic, but there are examples of when the polar curve is, say, two arcs of two conics and a line. One arc of a conic and two lines. And there is an example when the polar curve is composed of three conics. So if you think about this three web from the point of view of this sphere geometry, it is actually six web, because tangent plane intersect each of these three conics in two lines. So you have a six web. Then you can choose these arcs on each conics independently, and actually you have a 8 3 subwebs of 6 web. And this is a example of Wunderlich from the paper I mentioned in the very beginning. So maybe this is the most complicated examples known. Well, complicated from the point of view of
Sergey, sorry. So when you have this three conics, you have six web, right? Is it true that for this example, all three subwebs are hexagonal?
I have not checked this. I believe it's not.
Okay.
My conjecture is that this web may be of maximal possible rank, but I doubt that you can choose this. Well, you have three conics and you have a tangent line intersecting in 6 points, right? So you can choose the arcs, one on each of the conics independently, one from this, and one from this. So you have 8. Well, I think if it was the case, Wunderlich would not miss it. Actually, all this paper was password. All his paper was devoted to this 6 web actually. All right, let's consider the other example. So the second example, you will see it's symmetric with respect to rotation. Well, you have natural geometric invariance. Plane of the conic can miss the Darboux quadratic, can be tangent, and can cut it. So this invariant. And of course, the position of the polar line. It can be elliptic, hyperbolic, or parabolic. So the next examples is not symmetric. 3. So you see here is shown also the cyclic. Cyclic is envelope of a family which corresponds to conic. Actually, this remarkable example of Wunderlich, all the circles of the web are double tangent to some cyclic. It can be constructed in this way. So the next 4, you will see it's also symmetric by rotations, but the construction of the web is a bit different, right? I hope you see all the hexagons. Then the 5, you see this is also symmetric with respect to homothety. It's the rotation is symmetric. 6, I like the 6. It looks like some orthodox icon. So it's not symmetric. 7, it's also not symmetric. 8 is not symmetric. 9 is symmetric. You see, it's composed. Well, it's obtained by Wunderlich construction, but for the case when the generating curve is just one circle. If you move a circle by translation, a circle will pass any point 2 times, right? So actually the corresponding polar curve is a conic. So this one is not symmetric. The 10th, sorry. Number 10. 10. Then 11 was difficult to draw. I tried the different parameters, and that is the best I obtained. 11. 12. You see hexagons here. Some, well, actually, all the necessary discrete invariants are given in the title. So it's elliptic, parabolic, if the plane touches, intersects, or misses the Darboux quadratic, and the absence or presence of symmetry. So this is symmetric. This one was, I think I have seen in the book of Bляшke, Introduction to Web Theory. Well, this one is 13. 13 is made by concentric circles and tangent lines to one of these circles. It's hexagonal. 14th, this 14th was found by Nilov. There was a paper by Nilov in 2014. He has produced 5 examples. 4 of these examples are retrieved by this Shelikhov lemma, so they are in my classification, but one is not. So this one example of Nilov has as a polar curve 2 conics and a line. So actually it's 5 web. So it would be interesting also to compute its rank. 15th, also you see there is some envelope. It's actually the last one. So most of these examples, they depend on one parameter. So you project in the space of orbits, and most of them will be curves. So depending on one parameter. Only few of them are fixed actually. So there is only one orbit. Well, so I think this is all I wanted to present, and well, I probably would risk the conjecture that the polar curve, any component of polar curve is algebraic planar curve of degree of most 3. Well, this conjecture is based only on the known examples. I don't have some profound justification for this conjecture. So that's it.
Well, thanks a lot. Do you hear me? Жень, меня слышно? Видимо, нет. Давайте.
Да, слышно.
Ага, отлично.
Да, нормально слышно.
Okay, thanks a lot. It was very interesting and beautiful. Questions, remarks? Well, Женя asked a lot of questions. No remarks. Well, thanks a lot, Sergey. Thanks a lot again. And well, we'll meet in a week. Goodbye. Спасибо, очень красиво.